Welcome to today's explainer. You know, when we think about wind turbines, we usually just picture these serene, majestic white pillars, right? Just calmly turning in a gentle breeze. But consider this. The force of the wind doesn't just double when the wind speed doubles, it grows exponentially. So when that gentle breeze turns into a chaotic, howling storm, the atmospheric forces hitting that turbine are absolutely staggering. Let's dive right into this, because the engineering that prevents modern wind turbines from literally tearing themselves apart under all that immense pressure, it is absolutely brilliant.
So here's the core problem we're exploring today. How on earth do wind turbines survive extreme winds without just spinning completely out of control? I mean, think about it for a second. These machines are specifically built to capture the kinetic energy of the wind and turn it into mechanical power. But nature? Nature is wildly unpredictable. When wind speeds blow way past a turbine's safe limits, that same kinetic energy suddenly becomes a massive mechanical threat. We're talking forces strong enough to destroy the generator or literally snap blades the size of football fields right in half. No way around it, balancing that tremendous power is a constant, high-stakes game of physics.
The real magic of how they handle this actually happens hidden away inside that box, sitting right at the top of the tower. It's called the nacelle. Up front, you've got the rotor, which houses the hub and those massive blades. But the true unsung heroes here are the specific control mechanisms attached to them. Right where the individual blade meets the central hub, you have the pitch system. And down below that, connecting the whole nacelle directly to the main tower, is the yaw drive. These two areas, pitch and yaw, are the dynamic control centers. They literally dictate exactly how the entire turbine interacts with the incoming wind.
Okay, to really grasp how this whole thing works, we need to define one absolutely critical metric, the pitch angle, which engineers denote with the Greek letter beta. This is simply the angle between the axis of the blade and the direction of the incoming wind. Sounds simple, right? But this single angle is the absolute linchpin for understanding how turbines regulate power. It's effectively the turbine's throttle and its brake pedal, all combined into one single mechanism. By manipulating this specific angle, engineers can dictate exactly how much of the wind's power the turbine actually absorbs. This ensures it operates efficiently and, much more importantly, safely.
Think of the turbine blade just like an airplane wing. When wind hits it, the air travels faster over the curved upper surface than it does under the flat lower surface. This creates a pressure difference, lower pressure on top, higher pressure on the bottom, and that's what generates the aerodynamic lift, or torquing force that actually spins the rotor. So by controlling that pitch angle, beta, we're actively managing that exact pressure difference. We can increase the speed of the turbine, decrease it, or, if things get really dicey, even safely feather the blades to a complete dead stop by setting beta to 0.
Section 1. Directional Control, the yaw system.
So we know how the blades catch the wind, but let's be real, the wind rarely blows from just one perfect direction. That's exactly where the yaw system comes in. You can think of it as the neck of the wind turbine. Its entire job is to constantly pivot the massive nacelle to keep the rotor blades facing perfectly perpendicular to the wind. That ensures the turbine captures the maximum possible power. It uses an electrical motor and these heavy-duty gears to physically rotate that multi-ton housing. But once it's facing the wind, the yaw breakers clamp down like giant parking brakes, firmly locking the whole thing in place so it stays incredibly stable while it's operating.
Section 2. Speed Control, the stall phenomenon. Okay, so the yaw system keeps the machine pointed right at the wind. But what happens when that wind is blowing dangerously fast? Well, if you know anything about aviation, you know that an aerodynamic stall is pretty much a pilot's worst nightmare. It's when a wing loses its lift and just drops out of the sky. But for wind turbines, a stall is actually a highly intentional, totally brilliant safety feature. When wind speeds exceed those safe operating limits, the smooth flow of air over the blade gets intentionally broken up. It becomes highly turbulent. This turbulence dramatically decreases the torquing force, which slows the rotor down and ultimately saves the machine from ripping itself to shreds.
Now, there are two main ways to actually achieve this protective turbulence. First up is passive stall. In this setup, the blades are rigidly fixed to the hub, absolutely no moving parts. The blade is masterfully sculpted so that at safe wind speeds it captures power perfectly. But the moment the wind crosses a dangerous threshold, the physical shape of the blade naturally forces the air to become turbulent and stall. The downside? You do get some noticeable power fluctuations. Then we have active stall. Here, mechanical motors inside the hub actively rotate the entire blade, physically changing that pitch angle, beta, to intentionally force a stall exactly when it's needed.
Let's look a bit closer at how active stall behaves mechanically. To trigger an active stall, the system actually turns the blades directly into the wind. In technical terms, it mechanically increases the pitch angle, beta. By tilting the leading edge upward into the rushing air, it deliberately disrupts the aerodynamics, creates a massive pocket of protective turbulence, and safely caps the output power at its rated value, even if you're in the middle of a howling gale. It's basically like throwing an aerodynamic wrench into the gears just to slow things down.
Section 3. Speed Control, the pitch system.
Now, this final control mechanism operates on an entirely opposite aerodynamic principle to stalling. Instead of turning the blade into the wind to create all that messy turbulence, pitch angle control does the exact opposite. When extreme winds hit, it turns the blades out of the wind. It mechanically decreases the pitch angle, beta. This smooths out the airflow but significantly reduces the pressure on the lower surface of the blade. It gracefully decreases the torquing force, keeping the rotor speed safely dialed in without having to rely on violent air disruptions.
So it really all comes down to how we handle those extreme winds. Passive stall relies entirely on fixed geometry. It's simple, but it leads to those power fluctuations. The real mechanical battle is between active stall and pitch control. Active stall fights the wind by turning into it, increasing beta to cause turbulence. Pitch control, on the other hand, gracefully yields to the wind by turning out of it, decreasing beta to shed the pressure. And today, pitch control is the overwhelming industry standard. Why? Because simply yielding to the wind creates far less mechanical stress on that massive turbine structure than trying to fight it with heavy turbulence.
Just think about this for a second. Every single second of every day, inside the nacelle of a modern turbine, yaw systems are tracking the wind's every minor shift, while pitch systems make constant micro-adjustments to the angle beta. It is a stunning, real-time dance of fluid aerodynamics and heavy machinery, all working harmoniously to harness a hurricane and quietly power our homes. But it definitely leaves you wondering, as we build these turbines larger than skyscrapers to power our future, just how much more extreme weather can this delicate engineering dance truly withstand? Thanks for joining me for this explainer.